Have you ever wondered what happens to wood as it burns? It seems as if the wood may disappear into thin air. While burning wood appears to create energy and destroy the wood, they're not created or destroyed. Rather, energy and matter are changing from one form to another. You see, wood contains what we call chemical potential energy. Energy stored in the bonds that hold the chemicals together. This stored energy is released in the form of heat and light when the wood is burned. Wood also contains matter, where matter is anything that has mass and takes up space. The matter within the wood is transformed into different matter, including ash and soot, as it burns. The total amount of energy and matter in the wood before burning is equal to the energy and matter of the ash, soot, heat, and light after burning. In other words, energy and matter are conserved, both during and after the wood is burned. This phenomenon of conservation is explained by what we call the First Law of Thermodynamics, sometimes referred to as the Law of Energy Conservation. The law states energy cannot be created or destroyed. Energy can be described as the ability to do work, where work is the movement of matter when a force is applied to it. With the example of burning wood, the energy we see in the form of fire is not created out of nothing, but rather comes from the energy that is stored in the wood. Likewise, the wood is not destroyed, but rather converted into ash and soot. In order to better understand the law of energy conservation, we need to consider the fact that it applies to systems. A system is simply a collection of component parts that make up a whole. Burning wood is a system that includes the wood, heat, ash, and soot. The universe is the largest system that we know of, and it includes all matter and all energy, including the burning wood that we're talking about. There's other examples of small systems. For example, you can consider your body as a system. When you're cooking, you could consider a pot of water on the stove as a system as well. Now that we have a good understanding of systems, let's consider the difference between an open and a closed system and discuss the law of energy conservation as it applies to each. A closed system is a system in which no matter or energy is allowed to enter or leave. The first law of thermodynamics tells us that the amount of energy within any closed system is constant. It doesn't change. An open system, on the other hand, allows stuff to come in and go out, like burning wood in a fireplace. Here, you can add wood to the fireplace and light it with a match from, say, your pocket. Heat, ashes, and soot leave the fireplace as the fire burns. In other words, energy and mass can enter and leave a system as long as it comes from a system or leaves to go to another system. It's important to note, however, that the total mass and energy in our universe remains constant. Since most systems are not closed, the law of energy conservation can be rephrased to say that the change in the internal energy of the system is equal to the difference between the amount of energy coming in minus the amount of energy going out. In other words, the amount of energy in a system can change, but only if it comes from another system or goes to another system. At any rate, systems, whether they're open or closed, do not create or destroy energy. Rather, energy can enter from one system and leave to another.
All right, you've seen the first law of thermodynamics. This is what it says. Let's see how you use it. Let's look at a particular example. This one says, let's say you got this problem, and it said 60 joules of work is done on a gas, and the gas loses 150 joules of heat to its surroundings. What is the change in internal energy? Well, we're going to use the first law. That's what the first law lets us determine. The change in internal energy is going to equal the amount of heat that's added to the gas. So let's see, heat added to the gas. Well, it says that the gas loses 150 joules of heat to its surroundings. So that means heat left the gas. So heat left the gas. This must have been put into a cooler environment so that heat could leave. And so it lost 150 joules. A lot of people just stick 150 here. It's got to be negative 150 because this Q represents the heat added to the gas. If you lost 150 joules, it's negative 150. And then plus, all right, how much work was done? It says 60 joules of work is done on a gas. So that's work done on the gas. That means it's a positive contribution to the internal energy. That's energy you're adding to the gas. So 60 joules has to be positive. And so this is plus, the work done is positive 60 joules. Now we can figure it out. The change in internal energy would be negative 90 joules. But why do we care? Why do we care about the change in internal energy of the gas? Well, here's something important. Whether it's a monatomic or diatomic or triatomic molecule, the internal energy of the gas is always proportional to the temperature. This means if the temperature goes up, the internal energy goes up. And it also means if the internal energy goes up, the temperature goes up. So one thing we can say, just going over here, looking that the change in internal energy was negative. This means the internal energy went down by 90 joules. Overall, when all was said and done, this gas lost 90 joules of internal energy. That means the temperature went down. That means this gas is going to be cooler when you end this process compared to when it started. Even though you added 60 joules of work energy, it lost 150 joules of heat energy. That's a net loss. The temperature is going to go down. So this is an important key fact. Whatever the internal energy does, that's what the temperature does. And it makes sense since we know that an increase in internal energy means an increase in translational kinetic energy, rotational kinetic energy, vibrational energy. That temperature is also a measure of that internal energy. Note that we cannot say exactly how low the temperature went. This is a loss of 90 joules, but this doesn't mean a loss of 90 degrees. These are proportional, they're not equal. If I go down 90 joules, that doesn't mean I go down 90 degrees. I would have to know more about the makeup of this gas in order to do that. But the internal energy and the temperature are proportional. Let's try another one. Let's say a gas started with 200 joules of internal energy, and while you add 180 joules of heat to the gas does 70 joules of work. What is the final internal energy of the gas? All right, so the change in internal energy equals Q. Let's see, gas starts with 200 joules of internal energy, that's not heat. While you add 180 joules of heat, here we go, 180 joules, should it be positive or negative? It's going to be positive. You're adding heat to that system. So positive 180 joules of heat are added, plus the amount of work done on the gas. It says the gas does 70 joules of work. So most people would just do, all right, 70 joules. There we go. But this is wrong. This is wrong because this is how much work the gas does. This W up here with the plus sign represents how much work was done on the gas. If the gas does 70 joules of work, negative 70 joules of work were done on the gas. You have to be really careful about that. So we can find the change in internal energy. In this case, it's going to equal positive 110 joules. But that's not our answer. The question's asking us for the final internal energy of the gas. This is not the final internal energy of the gas. This is the amount by which the internal energy changed. So we know the internal energy went up because this is positive, and this is the change in internal energy. Internal energy went up by 110 joules. That means temperature is also going to go up. So what's the final internal energy of the gas? Well, if the internal energy goes up by 110 joules, and the gas started with 200 joules, we know the final internal energy, U final, is just going to be 200 plus 110 is 310. Or if you want to be more careful about it, you can write this out. Delta U, we can call U final minus U initial. That's what delta U stands for. U final is what we want to find, minus U initial is 200. So positive 200 joules was what the gas started with, equals, that's the change, and that's what we found, 110 joules. Now you solve this for U final, you would add 200 to both sides, and again, you would get 310 joules as the final internal energy of the gas. Let's look at one more. Let's say you got this one on a test, and it said that 40 joules of work are done on a gas, and the internal energy goes down by 150 joules. What was the value of the heat added to the gas? Note, we're not solving for the internal energy this time, or the change in internal energy. We're trying to solve for the heat. What's heat? Heat is Q. So this time we're going to plug in for the other two and solve for Q. What do we know? 40 joules of work are done on a gas. So this work has got to be a positive 40. because the work is done on the gas and not by the gas. And we know the internal energy goes down by 150 joules. It means the change in internal energy has to be negative 150. So if I plug in here, my delta U, since my internal energy went down by 150, delta U is going to be negative 150. Q, we don't know. So I'm just going to put a variable in there. Q, I don't know. I'm just going to put a Q in there. I'm going to name my ignorance and I'm going to solve for it. Plus the work done. We know the work done was 40 joules and it's positive 40. Positive 40 because work was done on the gas. Now we can solve for Q, the amount of heat. The value of the heat added to the gas is going to be, if I move my 40 over here, I subtract it from both sides, I'm going to get negative 190 joules. This means a lot of heat left. 190 joules of heat left the system in order for it to make the internal energy go down by 150 joules. And that makes sense. 40 joules of work were added, but we said the internal energy went down. That means the heat has to take away not only the 40 that you added, but also another 150 to make the energy go down overall. So the heat taken away has to be negative 190 joules. All right, so those were a few examples of using the first law. Basically, got to be careful with your positive and negative signs. You got to remember what these things are, that Q is the heat, W is the work, delta U is the change in the internal energy, which, don't forget, that also gives you an idea of what happens to the temperature.
Systems are extremely important in science, especially physical systems. They're a way to focus in on the exact thing you're really interested in and to help simplify the situation. But before we get into the details of how it works, we should first ask the question, what exactly is a physical system? A physical system, in general, is a set of connected parts that together form a cohesive whole. They're the parts that work together to do a job, or the parts that are simply connected together because they happen to be in contact with one another. A physical system is the part of the world you're focusing on and trying to explain. For example, let's say that you're studying the movement of the pendulum in a grandfather clock. Are you looking at the motion of the pendulum bob itself? Are you interested in the string as well? What about the place where the string connects to the clock? Exactly what part are you studying? Deciding that might make a big difference as to how complicated the results will be. The bigger the system, the more complex it tends to be. When you make the decision on what to focus on, we say you are defining the system. Systems can either be open or closed. A closed system is one where a quantity or series of quantities cannot enter or leave the system. For example, a system might be closed to energy, meaning energy might not be able to enter or leave the system. A vacuum thermos flask does a really good job of stopping energy from leaving the system to keep your drink warm. So it might make sense to treat it as a closed system. But no system in the real world is ever perfectly closed, so it will only be an approximation. The opposite of a closed system is an open system. An open system is one where a quantity or series of quantities can enter or leave the system to a significant degree. If you pour your hot drink into a mug instead of a vacuum thermos flask, the heat will escape relatively quickly into its surroundings. So a mug is most certainly an open system. Open systems are a lot more complicated to understand than closed.
So in our last video, we were talking about systems. We're going to see the type of systems, we're going to see the boundaries and the examples I'm going to present you, the surroundings, and what will be the universe. Closed system is essentially, there's no mass exchange, but you can exchange energy. Example, this can. Let's say you have your soda here, even though you know that the material is or will be always inside, you know that the heat can increase the temperature, or maybe if it's cold outside, you're going to decrease the temperature. So you can actually change heat. And the surroundings will be all that is not our can. So for example, the air on the ambient, this desk, maybe the table, or if it's in the fridge, and the universe will be, of course, all that is not, or actually, our little can and all the surroundings. Open system is a very common system in engineering. There is exchange of mass and energy. For example, this, I want to stick with the example of the beverage. You have this glass. It is not closed, actually. Your CO2 or the carbonation is going to go out. You could also be adding, I don't know, a mosquito or dust, or I don't know, whatever thing it might go inside. Then what else? You're going to have interaction with the outside world, with the heat. Let's say the ambient temperature is going to take away heat, or not give heat. It's going to hot or to heat and increase this into a hot state, etc. And last but not least, insulated system is in theory impossible, but we can achieve that. And why impossible? Because there is no change of energy, and that does not happen in real life. This one may happen a little bit, you can say in general, but energy is more difficult. And I will say that, let's say we have our coffee here, it's hot, Celsius, 100 Celsius, and outside is 25 Celsius. And let's say there is no change because this is very awesome material that does not exchange temperature with the outside. So there's my coffee. Let's say there are 100 grams of coffee inside. Actually, it will be 100 milliliters of coffee. I'm saying it's about 100 grams of coffee. And it's about 100 Celsius, and it will not exchange energy. So the actual heat energy of my coffee stays the same. And that's about the systems. We are going to use only 3 systems.
On a cold winter day, Amy decides to build a fire in her living room fireplace to warm up. Soon, the fire is burning brightly and the room is much warmer. As Amy enjoys the warmth from the fire, she wonders what is happening to heat the air around her. According to the kinetic theory of gases, all gases are made up of microscopic molecules that move in straight lines until they bump into another gas molecule or object. In Amy's living room, the energy from the fire is being transferred to these air molecules. This transfer of energy causes them to move around faster and bump into each other more. Kinetic energy is proportional to the speed of the molecules. As the speed of the colliding molecules increases, so does the total kinetic energy of all the gas molecules. It's pretty difficult to measure the speed of an individual gas molecule. Instead, temperature can be used as a measure of the average kinetic energy of all the molecules in the gas. As the gas molecules gain energy and move faster, the temperature goes up. This is why Amy feels warmer. To determine the average kinetic energy of gas molecules, we need to know the temperature of the gas, the universal gas constant, R, and Avogadro's number. K equals 3/2 times R over N sub A, all times T. Let's assume that it is 75 degrees in Amy's living room right now. What is the average kinetic energy of the air molecules in the room? First, we need to convert the temperature of the room from degrees Fahrenheit to Kelvin. 75 degrees Fahrenheit is equal to 297 Kelvin. Remember that R and K are constants. So to calculate the average kinetic energy, we just need to know the temperature. Use this formula to calculate the average kinetic energy as follows. K equals 3/2 times 8.314 joules per mole K over 6.022 times 10 to the 23rd power atoms per mole, all times 297 K. Therefore, the average kinetic energy of each molecule is 6.15 times 10 to the negative 21st power joule. As temperature and average kinetic energy increases, so does the average speed of the air molecules. However, all the molecules are not moving at exactly the same speed. One way to get an approximation of the average speed of the molecules in a gas is to calculate something called the mean squared, or RMS speed. The RMS speed of the molecules is the square root of the average of each individual velocity squared. For example, if 3 objects had speeds of 10 meters per second, 5 meters per second, and 7 meters per second, respectively, then the RMS speed of the group would be 7.6 meters per second. Of course, in Amy's living room, there are a lot more than 3 particles of gas. V sub RMS equals the square root of V1 squared plus V2 squared plus V3 squared divided by 3. V sub RMS equals the square root of 10 meters per second squared plus 5 meters per second squared plus 7 meters per second squared divided by 3. V sub RMS equals 7.6 meters per second. Since particles in motion have kinetic energy, and kinetic energy increases with speed, there is a relationship between the RMS speed of gas molecules and the average kinetic energy in the gas. This means that there is also a relationship between RMS speed and temperature. The average kinetic energy, K, is equal to 1/2 of the mass, m, of each gas molecule times the RMS speed squared. K equals 1/2 m V sub RMS squared, where m equals the mass, V sub RMS equals RMS velocity, and K equals kinetic energy. So, what is the RMS speed of the gas molecules in Amy's living room? Remember that the average kinetic energy was 6.15 times 10 to negative 21st power joules per atom. Although air in Earth's atmosphere contains lots of different gases, almost 78% of the atmosphere is nitrogen. Therefore, we will use the mass of a molecule of nitrogen, N2. Since a molecule of nitrogen gas contains 2 nitrogen atoms, we can find the mass of a molecule by first multiplying the atomic mass of a single nitrogen atom, 0.014 grams per mole, by 2 to get a molecular mass of 0.028 grams per mole. Next, divide by Avogadro number to determine that the mass of a single molecule of nitrogen gas is 4.65 times 10 to the negative 26th power kilograms. M equals 0.014 kilograms per mole times 2 times 1 over 6.022 times 10 to the 23rd power atoms divided by mole. M equals 4.65 times 10 to the negative 26 power kilograms per atom. Once we have the mass of a nitrogen molecule and the average kinetic energy, we can solve for the RMS speed of the molecules in the room. K equals 1/2 m V sub RMS squared. 6.15 times 10 to the negative 21st power joule equals 1/2 4.65 times 10 to the negative 26 kilogram V sub RMS squared. V sub RMS squared equals 264,516 meters squared per second squared. V sub RMS equals 514 meters per second. Therefore, we can calculate that the RMS speed of the molecules in Amy's living room is about 514 meters per second. Pretty fast, right? If you don't know the individual speeds of each gas molecule, there is another way to determine RMS speed. One way to do this is to look at a graph that shows the distribution of speeds throughout the gas. Most of the gas molecules will have speeds that are close to the RMS speed, with proportionately fewer molecules moving at both higher and lower speeds. This gives the distribution of all the gas molecule speeds the shape of a bell curve. The peak of the bell curve will tell us the speed of which the majority of the molecules are moving, which corresponds to the RMS speed. Diffusion is the movement of molecules from areas of high concentration to low concentration. The rate at which gases diffuse depends on the temperature of the gas. As the temperature increases, the rate of diffusion increases. Why does this happen? Let's think of what we know about the relationship between temperature and the RMS speed of molecules. The temperature of a gas increases when the RMS speed of the molecule increases. When molecules are moving faster, they are able to spread out more quickly than at a lower temperature. According to the kinetic theory of gases, all gases are made up of microscopic molecules that move in straight lines until they bump into another gas molecule or object. Temperature is a measure of the average kinetic energy of all the molecules in a gas. K equals 3/2 times R over N sub A, all times T, as the temperature and therefore kinetic energy of a gas changes. The RMS speed of the gas molecules also changes. The RMS speed of the molecules is the square root of the average of each individual velocity squared. K equals 1/2 mv sub RMS squared, where m equals mass, v sub RMS equals RMS velocity, and K equals kinetic energy. Because speed changes with temperature, the rate of diffusion of a gas also depends on the temperature. Diffusion is the movement of molecules from areas of high concentration to low concentration. Diffusion occurs more quickly as temperature and kinetic energy increases.
Hello friends, here in this video we are going to see the application of First Law of Thermodynamics to non-flow system, also called as closed system. Let us get started. Now, in the application of First Law of Thermodynamics to non-flow system or closed system, first of all, a closed system is that system from which only energy can cross the boundary of the system, whereas mass, it cannot cross the boundary. So that is the definition of closed system. If we compare it with open system, in case of open system, both energy and mass can cross the boundary of the system, but here only the energy is going to cross the system, whereas mass will remain within the boundary of the system. Now, as far as the application is concerned, here we would be having 5 different processes which are the application of first law to closed system, and those are So here as I have written, there are 5 processes, or we can say 5 application of first law of thermodynamics to closed system. The first process is reversible constant volume process, in which the volume of the system remains constant. Next, there is reversible constant pressure process. It means the process would be taking place at a constant pressure. Next, there is reversible constant temperature process, also called as isothermal process, in which the temperature will remain constant during this process. Next, there is reversible adiabatic process, which will be governed by a law PV raised to gamma is equal to constant. And the last one is reversible polytropic process, which will be governed by the law PV raised to N is equal to constant. So these are the 5 applications of first law of thermodynamics to non-flow system or closed system. In the further part, we are going to see each of these explanation or applications in detail.
Have you ever touched a hot pan and burned yourself? How about warmed yourself in front of a nice campfire on a cold night? Ever notice that most of the time air vents in houses in the north are on the floor, while in the south they're on the ceiling? These are all related to the movement of heat and how it gets transferred between substances and locations. Heat can move between objects or spaces, and there are 3 main ways it does this: conduction, convection, and radiation. Let's look at how each one works. If someone pours you a hot cup of coffee, you're likely going to pick it up from the handle instead of around the main part of the mug. This is because the coffee mug will conduct heat from the hot liquid inside to your hand. This direct transfer of heat from one object to another is called conduction. The coffee mug transfers heat well, as do many other substances, including metal. You certainly wouldn't touch a hot metal pan on the stove or hold a nail over a flame without some sort of protective glove, because you know that the heat from metal will quickly transfer to your hand and burn you. It makes sense then that these substances that conduct heat well are called conductors. Some substances are very bad at transferring heat, and these are called insulators. Wood is a very good insulator, therefore a very poor conductor, which is why your metal pot on the stove may have a wooden handle. You can do a little experiment to see this in action. If you have an area in your house where wood floor meets some tile, put a bare foot on each one. You'll find that the tile floor feels cooler, but both floors are actually the same temperature. The tile is a much better conductor of heat than the wood, so it transfers the heat from the bottom of your feet better than the wood does, making your foot feel cold. Air is also a very poor conductor, which is why you can reach your hand inside an oven to grab a dish without burning yourself, unless you forget your oven mitts and grab the dish itself. Your house is insulated with something like rock wool or fiberglass because these substances are poor conductors of heat. Imagine how cold your house would be if there was no protection from the cold outside during winter, or how hot it would be if you weren't protected from the heat outside in the summer. Interestingly though, insulators don't actually stop the flow of heat, just slow the transfer considerably. That's why you still need to run your heat in the winter and AC in the summer, just not as much as if you had no insulation at all. Remember how I said houses in the north commonly have their air vents on the floor, while houses in the south have theirs on the ceiling? This is due to the way that heat flows in fluids, and both gases, like air, and liquids, like water, are considered fluids because of the way they move. When heat is transferred by currents in a fluid, this is called convection. Convection happens in all fluids, like the air in your home, water in a lake, and magma underground, just to name a few. Here's how it works. Imagine a room full of children who have just had a bunch of cookies. They become quite energetic and start running around the room. You open the door and let them outside, they burst out and start running around the larger space, spreading out in the yard. And the same thing happens when a fluid is heated. The molecules at the bottom gain energy and begin to move faster. As they move faster, they begin to spread apart, which makes the fluid less dense. But instead of being confined to a yard, the fluid's warmer molecules begin to move upward while the cooler, denser fluid begins to sink, just like the children start settling down as their cookie crush subsides. Once the cooler molecules reach the bottom where the heat is, it's like they ate another cookie and get an increase in energy again. They rise back up to the top while the cooler molecules sink back down to the bottom. The cycle continues as long as there is a heat source at the bottom. What does this have to do with air vents in a house? Well, if you live in a cold climate, you probably use your heat more often than your AC. And if you live in a warmer climate, you probably use your AC more than your heat. So if hot air rises and you use
When we observe what we call fire, we have this combustion reaction going on, and then we see these flames. What we're really observing are the three forms of thermal energy transfer. We're observing convection, and thermal radiation all at the same time. So it is thermal radiation. And I could say thermal conduction, thermal convection, and thermal radiation. The word thermal is just relating to things dealing with temperature. So what is the conduction going on? Well, what we have going on in the fuel for our fire, so down here, the fuel for our fire, we have our classic combustion reaction. And I encourage you to watch the video on that in our chemistry playlist or our chemistry section if you're interested in it. But you're taking carbon molecules and their bonds, and then in the presence of oxygen and some heat, you have a combustion reaction producing carbon dioxide and producing water, and even more energy than you put into it. So it's producing a lot of energy. And that energy is going to excite the molecules that are around it. So you have these molecules that end up getting a lot of kinetic energy. And remember, temperature is proportional to average kinetic energy. And so the ones that just combusted, or the molecules right near the reaction, or maybe the ones that were part of the reaction, they're going to have this really high average kinetic energy, because all of this energy was released from that combustion reaction. And then they're going to bump into other molecules that might not have quite as high kinetic energy, but then they're going to transfer that kinetic energy through these collisions. And we have a whole video on thermal conduction, but that's what's happening. Things with higher kinetic energy are bumping into things with lower kinetic energy and transferring some of that kinetic energy, and they're transferring some of that momentum. So that is definitely happening when we look at a fire like this, that neighboring molecules are bumping into other molecules and transferring energy. Now, convection, this is around the idea that hot air is less dense. And so if we have a bunch of air particles here, so let's say this is the cool air up here, and it makes sense why cool air is going to be more dense than hot air. Because hot air, these particles have a much higher kinetic energy. And so they're going to bump into each other, and they're going to push each other much further away and get more separation from each other because of that high average kinetic energy. But because the hot area is less dense, this area right over here is less dense, than the white area, these might all be the same molecule, I just made them in different colors to show the less dense area and the more dense area, it is going to rise. It is going to rise, or you could even think of it as the more dense area is going to fall around it, or try to go under it, because it is more dense, and then the less dense area is going to rise. And by doing that, you have the hotter molecules are moving upwards, and then the cold molecules can go down to maybe the source of energy right over here to get heated up more. So this right over here, so hot air rises. Let me write this. The hot air rises. And one way to think about it makes room for the cooled air to come down and then get heated up again. And that's what's going on in the fire here. You see the combustion reaction. Combustion reaction occurs right over there. Let me do this in a different color. Combustion reaction is occurring in the fuel. The super hot air, it's going to rise. And that's why it looks like these flames are they're moving upwards. They're kind of flickering upwards. And you'll also see, and actually we're going to talk about this in thermal radiation, is that they also change color as they move upwards. But this whole idea of fire moving upwards and the hot air, if you put your hand up here, it's going to be much hotter than if you were to put your hand, say, right here. Even though in theory this is closer to the flame than up here, and that's because the hot air is rising, and it's making room for cold air, or cooler air, I guess I could say, come down here and and get heated up again, and then it would rise up again. And so this convection, this idea of the hot air rising or the cold air falling, this is another form of heat transfer. Now, the last form that we're observing when we're looking at fire is thermal radiation. And this is all around the idea that if you have charged particles being accelerated, they're going to release electromagnetic radiation. And so you might say, wait, charged particles, where are those being accelerated here? Well, we have these molecules that are constantly being accelerated as they bump into each other. One's going to transfer kinetic energy from, let's say this one bumps into that, it's going to accelerate that in a different direction. And even this one might go in another direction, and acceleration is a change in velocity. So it could be the magnitude of velocity or your direction of velocity. So as they're colliding, you have all of these acceleration of charged particles. So let me write this down. You have acceleration of charged particles, and then that releases electromagnetic radiation. I know what you're thinking. Wait, hold on a second, Sal. I can buy that we have molecules that are being accelerated, but where are you getting this charged particles business? Well, we have to remember these molecules are made up of atoms, and atoms are made up of charged particles. They're made up of protons and electrons. And so as you accelerate these, and the more that you accelerate these, the more radiation you are going to release. And you might say, wait, okay, you said I'm observing that in fire. Where am I observing radiation? Well, just the very fact that you can see the fire, the light emitted from the fire, that is electromagnetic radiation. It's just the electromagnetic radiation in the wavelengths that your eye considers to be visible light, or that your eye considers to be light. Even the particles up here that are still quite hot, they are also emitting electromagnetic radiation because they're all bumping into each other, and their electrons and their protons are all getting accelerated in different ways. They're also releasing electromagnetic radiation, but it is at a slower wavelength than your eye is capable of perceiving as light. If you had an infrared camera, you would see the flames being much larger. You would see them go all the way up here. And if you were to look at the flame closely, you would see down here, right where the combustion reaction is happening, the flame looks blue. And that's because the blue light is higher energy light. And that's because the particles are being accelerated more down here. And then it goes from blue to kind of white, to a yellow, to a red, or to an orange, to a red. And then to your regular eyes, it disappears. But everything that has some temperature is releasing electromagnetic radiation. And you're like, okay, well, that's all fine. I can see it. But how is that a form of energy transfer? Well, if you've ever sat next to a flame, you will feel the heat. In fact, even if the air between you and the flame is cold, you would still feel like you're getting warm. So if this is a flame right over here, so that is fire. And let's say you have cold air cold air, let's say you're at a campfire right over here, maybe it's 30, this air right over here is 30 degrees. If you are standing right over here, you would still feel heat. You would still feel like you're getting warmed up. And that's because that electromagnetic radiation is being emitted from the air particles that we perceive as fire, and then that can actually excite particles on your skin, and it'll transfer energy to your skin, and so you feel like you are actually getting warmed up. I remember once, this is kind of a strange story, but I was on the highway, and there was a car on fire, and I was literally, we drove to the far lane because it was on fire. We're 3 lanes away from it, and it kind of exploded. I don't think anyone was in it. Hopefully no one was in it. But I remember right when it exploded, it was an intense, immediate heat that we felt through the window of the car. And that was electromagnetic radiation. That was thermal radiation being released by these accelerated particles in the air around that explosion, which we perceived as an explosion or fire, but then it was warming up particles on my skin.
Imagine you had a monatomic ideal gas in this cylinder here, and there was this tightly fitted piston above it that prevented any gas from getting out. Well, we know that the total internal energy for a monatomic ideal gas is just 3/2 P times V, or 3/2 NKT, or 3/2 little n RT. And we know that saying U internal, the internal energy, is really just code for the total kinetic energy of the monatomic ideal gas, that these are the same thing. When we talk about internal energy, we're talking about how fast are these particles moving. In other words, what's the total kinetic energy of all of these particles added up. My question is, how do we go about changing the internal energy? Let's say we wanted to increase the total kinetic energy. What could we do? Well, you could say increase the pressure or the volume or the temperature. Yeah, but I mean, physically, actually, in the lab, what do we do? And there's basically 2 ways to change the internal energy. If we want to add internal energy, i.e. get these particles moving faster, we can heat it up. So put this above a flame or on a hot plate, and heat will flow into the gas, which will cause these particles to move faster and faster. That's one way to do it, to add heat. The other way to do it is to do work on the gas. I could take this piston and push it down, and if you push this down hard enough, it'll squash this gas together, and those impacts with this piston while it's moving down will cause them to start moving faster and faster. That will also add internal energy to the gas. So if we wanted to write down a formula that told us how you could get a change in the internal energy, if I want to change the internal energy, delta U, which is really just saying changing the kinetic energy, well, there's 2 ways to do it. I can add heat. So if I added 10 joules of heat, I'd add 10 joules to the internal energy, but I've also got to take into account this work being done. And so I could do plus the work done on the gas, and that's it. This is actually the first law of thermodynamics. It's a law of conservation of energy. It says there's only 2 ways to add energy, internal energy, to a gas. Let me talk a little bit more about this work done though, because getting the sign right is important. If you're doing work on the gas, compressing it, you're adding energy to the gas. But if you let the gas push up on the piston and this gas expands, pushing the piston up, then the gas is doing work. That's energy leaving the system. So if the gas does work, you have to subtract work done by the gas. If the outside force does work on the gas, you add that to the internal energy. So you got to pay attention to which way the energy is flowing. Work done on gas, energy goes in. Work done by the gas, energy goes out, and you'd have to subtract that over here. Let's say the gas did expand. Let's say the gas in here was under so much pressure that the force it exerted on this piston was enough to push that piston upward by a certain amount. So let's say that it started right here and it went up to here. So that piston went from here to there. No gas is escaping because this is tightly fitting, but the gas was able to push it up a certain distance d. How much work was done? You know the definition of work. Work is defined to be the force times the distance through which that force was applied. So the work that the gas did was F times d, but we want this to be in terms of thermal quantities like pressure and volume and temperature. So what could we do? We can say that this volume, not only did the piston raise up, but there was an extra volume generated within here. That I'm going to call delta V. And I know that this delta V has got to equal the area of the piston times the distance through which that piston moved, because this height times that area gives me this volume right in here. Why am I doing this? Because look, I can write D as equal to delta V over A, and I can take this and I can substitute this formula for D into here, and something magical happens. I'll get work equals F times delta V over A. But look, F over A, we know what F over A is, that's pressure. So I get that the work done by the gas is the pressure times delta V. This is an equation that I like because it's in terms of thermodynamic quantities that we're already dealing with. So work done, you can figure out by taking P times delta V. But strictly speaking, this is only true if this pressure remained constant, right? If the pressure was changing, then what am I supposed to plug in here? The initial pressure, the final pressure? If the pressure is staying constant, this gives you an exact way to find the work done. You might object and say, wait, how's it possible for a gas to expand and remain at the same pressure? Well, you basically have to heat it up while the gas expands. That allows the pressure to remain constant as the gas expands. And now we're finally ready to talk about heat capacity. So let's get rid of this. And heat capacity is defined to be, imagine you had a certain amount of heat being added. So a certain amount of heat gets added to your gas. How much does the temperature increase? That's what the heat capacity tells you. So capital C is heat capacity, and it's defined to be the amount of heat that you've added to the gas divided by the amount of change in the temperature of that gas. And actually, something you'll hear about often is the molar heat capacity, which is actually divided by an extra N here. So instead of Q over delta T, it's Q over N, the number of moles times delta T. Pretty simple, but think about it. If we had a piston in here, are we going to allow that piston to move while we add the heat, or are we not going to allow the piston to move? There's different ways that this can happen, and because of that, there's different heat capacities. If we don't allow this piston to move, if we weld this thing shut so it can't move, we've got heat capacity at constant volume, and if we do allow this piston to move freely while we add the heat, so that the pressure inside of here remains constant, we'd have the heat capacity at constant pressure. And these are similar, but different, and they're related, and we can figure them out. So let's clear this away. Let's get a nice, here we go, 2 pistons inside of cylinders. We'll put a piston in here, but I'm gonna weld this one shut. This one can't move. We'll have another one over here that can move freely. So over on this side, we'll have the definition of heat capacity. Regular heat capacity is the amount of heat you add divided by the change in temperature that you get. So on this side, we're adding heat. Let's say heat goes in, but the piston does not move. And so the gas in here is stuck. It can't move. No work can be done. Since this piston can't move, external forces can't do work on the gas, and the gas can't do work and allow energy to leave. Q is the only thing adding energy into the system, or in other words, we've got heat capacity at constant volume is going to equal, well, remember the first law of thermodynamics said that delta U, the only way to add internal energy or take it away is that you can add or subtract heat and you can do work on the gas. In this case, Q, if I subtract W from both sides, I'd get delta U minus W over delta T. But since we're not allowing this piston to move, the work done has got to be 0. So there's no work done at all. So the heat capacity at constant volume is going to be delta U over delta T. What's delta U? Let's just assume this is a monatomic ideal gas. If it's monatomic, we've got a formula for this. Delta U is just 3/2 P times V over delta T. But that's not the only way I can write it. Remember, I can also write it as 3/2 N K delta T. over delta T, and something magical happens. Check it out. The delta T's go away, and you get that this is a constant, that the heat capacity for any monatomic ideal gas is just going to be 3/2 capital N K, Boltzmann's constant. N is the total number of molecules, or you could have rewrote this as little n r delta T. The T's would still have canceled, and you would have got 3/2 little n, the number of moles, times r, the gas constant. So the heat capacity at constant volume for any monatomic ideal gas is just 3/2 nr. And if you wanted the molar heat capacity, remember that's just divide by an extra mole here, so everything gets divided by moles everywhere. Divided by moles, that just cancels this out, and the molar heat capacity at constant volume is just 3/2 r. So that's heat capacity at constant volume. What about heat capacity at constant pressure? Now we're going to look at this side. Again, we're going to allow this gas to have heat enter the cylinder, but we're going to allow this piston to move up while it does that so that the pressure inside of here remains constant, and this is going to be the heat capacity at constant pressure. Well, again, we're going to get that it's Q over delta T, and just like the first law said, Q has to equal delta U minus W, so we get delta U minus W, the work done, over delta T. This time W is not 0. What's W going to be? Remember, W is P times delta V. So this is a way we can find the work done by the gas, P times delta V. So this is going to equal delta U. We know what that is. If this is, again, a monatomic ideal gas, this is going to equal 3/2 N R delta T plus, this is P times delta V, but we have to be careful. In this formula, this work is referring to work done on the gas. But in this case, work is being done by the gas, so I'd need another negative. Technically, the work done on the gas would be a negative amount of this, since energy is leaving the system. So that negative cancels this negative, and I get plus P times delta V, all of that over delta T. Whew. So what do we get? 3/2 NR delta T plus, I want to rewrite P times delta V, but I know how to do that. The ideal gas law says PV equals nRT. Well, if that's true, then P times delta V is going to equal NR delta T. So I can rewrite this as NR delta T divided by delta T, almost there. All the delta T's go away, and look what I'm left with. I'm left with C. Heat capacity at constant pressure is going to be equal to 3/2 NR plus NR. That's just 5/2 NR. And if I wanted the molar heat capacity, again, I could divide everything around here by little n, and that would just give me the molar heat capacity at constant pressure would be 5/2 R. And notice they're almost the same. The heat capacity at constant volume is 3/2 NR, and the heat capacity at constant pressure is 5/2 NR. They just differ by NR. So the difference between the heat capacity at constant volume, which is 3/2 NR, and the heat capacity at constant pressure, which is 5/2 NR, is just CP minus CV, which is NR, just NR. And if you wanted to take the difference between the molar heat capacities at constant volume and pressure, it would just be R. The difference would just be R because everything would get divided by the number of moles. So there's a relationship, an important relationship, that tells you the difference between the heat capacity at constant pressure and the heat capacity at constant volume.